Hello, everyone. Thanks for joining our talk. So my name is Jinyang, and we also have my teammate Tingting here. We are both software engineer from the data warehouse infra team at Airbnb. And today we will share you with some our most common issues for managing the interactive workload on Trino and how we solve the problem. Now I'm going to hand over to Tingting to talk first.
Hello, everyone. My name is Tingting. First, let me provide some background on our data warehouse architecture and Trino setup. This picture illustrates the architecture of the offline data warehouse in Airbnb. On the top, we have different clients including Superset, Tableau, CLI, Airflow, Java services, and Notebook. Users and services interact with data warehouse through these clients. In the middle, we have Spark, Hive, Hive Server 2, and Flink running on EMR. And we have Druid, Trino, and Starrocks as query engines. In the bottom, we store our data on S3 as Iceberg and Hive tables, also a small percentage of others. Trino is mainly used for interactive analytics and empowers Superset dashboard as it's fast and easy to use. We have approximately 1,200 distinct human users using Trino every day, and it also serves queries from data pipelines. Now let's zoom into Trino setup. This picture shows how we set up Trino in Airbnb and how Trino interacts with other components. For clients, we have the same clients as shown in the previous picture. For Trino, we have a proxy layer on top of Trino clusters and multiple Trino clusters behind it. Clients need to connect to the proxy through Kerbals. Our Trino clusters and proxy are all running on Kubernetes. We also have Ranger and our internal access control system. In addition, Trino emits metrics to Datadog and uploads logs to Kibana for observability. Underlying, we store data on S3, and we also have Metastore on top of it. Now let's take a look at why interactive workloads is important when managing Trino clusters. Interactive queries here means queries sent from human users, not from Airflow or other services. Here is a chart showing the percentage of number of interactive queries running on different engines in July. Though some people run interactive queries on Spark SQL or Hive, the majority of people use Trino since it provides much better performance. From past experience, we noticed that a lot of problems are caused by very large queries. Then we collect data from the past and learned that usually these problematic queries have high CPU usage. If we use 1 hour CPU usage as a threshold, we can put the queries into two categories. CPU usage below this threshold are small queries and others are large queries. And even though there's only around 2% large queries among all, surprisingly, they use around 92% of CPU use resources. And that is why large queries can often cause problems. Now let's take a look at two typical problems we see on Trino. In the first scenario, a user comes to our channel asking, I submitted a very simple query, why did it take so long to finish? We look at the cluster and found this user submitted a very large query before the small one, and it blocks his small query. Imagine Trino cluster is a highway. The large trucks are running slower than small cars. When you are following a truck, you will also be slow. In another scenario, a user asks, why my query fails, and the error says there's an internal error. We checked the cluster and found there's a sudden spike of workload, and it causes the whole cluster to be overloaded. In this case, there are too many large trucks on the highway and might cause collisions and damages. To summarize the common issues we observe from these examples, also these are the issues in other interactive compute engines as well. An interactive query can be very large. It could use 300 more compute resources than small pipeline queries on average. The workload can be spiky and fluctuate throughout the day. For example, there are more users running queries and opening dashboards in mornings and less people running queries at night. Since we do not have a very good intra-cluster isolation mechanism, the resource of a cluster with 200 nodes can be easily taken by only a few, like 10 large queries. And cluster scale-ups takes time and does not meet the expectation of interactive queries. Previously, we tried a few alternatives. For example, we create several clusters and route the queries to different clusters based on where it comes from. We have an interactive cluster for ad-hoc queries, batch cluster for pipeline queries, and a dashboard cluster for superset queries. But this doesn't solve our fundamental problem. Workload on the cluster can be unbalanced. While one cluster is idle, another cluster may suffer from blocking traffic or overloaded workload. An ideal scenario on the highway will be trucks and small cars have separate lanes. In this case, small cars can run faster. As for queries, we need to know the size of a query before we run it on the cluster. Then we need to have a scheduling method to schedule it based on its size and priority. In this way, small queries can be prioritized and get scheduled sooner. This also helps to improve the overall performance in the whole cluster. Summary from this, we need to understand the workload and improve scheduling. These are the two keys to solve the problem for managing interactive queries. Next, I'm going to hand over to Jinyang to talk about our new architecture.
Yeah, thanks, Tingting. So very great summary. So the key point to solve the problem is to understand the workload and also improve the scheduling. So next, I'm gonna talk about what is our new architecture to managing the Trino workload and how is our result looks like. With the old architecture, users submit query to the gateway proxy, and the proxy will forward the query to a backend Trino cluster based on the query source. For example, queries from superset SQL Lab are always being forwarded to the interactive cluster because they are categorized as the interactive workload. Airflow pipeline queries are always routed to the pipeline cluster, and superset dashboard are always routed to the superset dashboard cluster. This three cluster structure can provide some level of isolation. However, the noisy neighbor and spiky workload issue we mentioned above remain unresolved within each cluster. To handle the workload problem, we now introduce a new component called workload forecast. It will estimate the query size before routing to a physical Trino cluster, and the query routing will not only looking at the query source, but also take the query size and priority into consideration. The underlying Trino cluster will coordinate together to process the query with different sizes and priorities. Next, we will look deeper into how we create a workload forecasting service. To forecast the Trino workload, there are two options. In the first option, we can use the query engine's planner and get an estimation on the query cost. During the query planning generation, planner estimates the query cost based on the data size on each stage and the complexity of the operation. The estimation process is defined by the planning logic. From the plan, we can not only see how expensive the Trino query is, but also understand which stage has the highest cost. One limitation of this solution is if the estimation is wrong for one query type, fixing the logic will be extremely difficult. Another option is to use the machine learning model to learn from the historical query stats. This approach doesn't require any deep understanding of the query engine internal, and it can be easily applied to different query engines. All we need to do is to collect enough query execution samples to train the model properly. Since we operate the Trino cluster by ourselves, collecting enough training data is not a problem. Luckily, the workload pattern for the offline data analytics queries doesn't change frequently. So this also making a machine learning model a good fit. So in the end, we pick the machine learning option as the query forecasting method. With the past historical data runs, predicting a new query cost is a classification problem. We will provide a query as input. Model should tell us if a query is large or small. Let's look at how we can use a machine learning model to predict the query cost in 5 steps. So first, we found that, okay, the SQL string text is very hard for models to learn. We need to parse the SQL into a query statement tree, which is easier to process programmatically. The query statement tree describes the query better than the SQL string, but sometimes the query statement tree could be very complicated and cannot be directly used as the input for a machine learning model. To simplify this problem, we should only keep the components that have big impact on the query cost and ignore all the rest nuances. Here we introduce a new element called query features, which are the key signature of a query. We will use the query features to classify a query. Just like a car may have multiple features, a query may also have multiple features. Some common features we care about include input tables, joins, group by, and limits. These features are most important components of a query and can mostly describe what a query looks like. And next, after extracting this feature from a query, we will further simplify them into numbers, presenting how many times the feature shows up in the query. Now we have an integer array describing the query, and the array can be easily used as a machine learning model input. With a proper input, now we can use the model to run the prediction and then tell us what's the estimation of the query cost. In this project, we explored two popular models. The first model we evaluated is the k-nearest neighbors. When a new unknown instance comes in, the most straightforward way to find out the estimation cost is to find out those instances with the most similarity from the known group. KN maintains an in-memory tree and uses proximity to make the classification. We send a new instance to the KN, and it tells us who are the nearest neighbors. With those nearest neighbors, then we can use the average or median of the neighbors' values to make a prediction. The second model we evaluated is the XGBoost. XGBoost maintains a decision tree based on the existing training data. Each level will evaluate a feature and then add a prediction score. In this slide, we use a join as an example. So XGBoost analyzed the training data and learned that, okay, the query with joins are more likely to be larger queries. So when testing a new input, it will assign a higher prediction score for input with joins comparing to the input without joins. And similarly, grouping by, order by will also contribute to the prediction score. There are multiple levels of trees to evaluate the different features, and in the end, it will classify the input and tell us if it's more likely to be a small query or a large query. Unlike the KN returns who are the similar instances, XGBoost gonna return the output value directly. We experimented both models with real Trino query traffic, and found out that each model has its own advantage and disadvantages. KN is simpler and more transparent. And for every input, we can clearly see why the test data is closer to a group of instances. Therefore, we can understand the reason of the classification. Whereas the XGBoost is more like a black box. It's very difficult to understand the internal mechanism. And KN requires some tunings. This is because each feature may have different weight, and it will impact the instance distance. In comparison, XGBoost generates this decision tree by itself automatically. Not much of the manual tuning is required. And KN is going to use less compute resource, mainly because the KN model can be used for one KN model can be used for multiple attributes. After finding the nearest neighbor with a prediction, we can get both the CPU time and memory estimation by averaging the neighbors at the same time. But because XGBoost returns the output value directly, we need to separate models for each prediction attribute. Therefore, requires more compute resources. During the experimentation, we found that XGBoost has more accuracy than the KN on the query cost prediction problem space. And in the end, XGBoost is selected for our workload forecasting module, mainly because it has a higher accuracy rate. And now, models give us the forecast result with CPU time and peak memory size. The cost information will be used to route the traffic properly. And finally, after query execution on a backend Trino cluster, the fitness stats will be saved to a database and then reported back to the forecasting module. The feedback loop can provide the latest query pattern and further improve the prediction accuracy for the future use. And this picture is a high-level architecture overview of our query workload forecasting service. Forecasting service take the SQL as input, generate the CPU time and peak memory estimation as the output. Query engine will run the query and then report the stats back after real query execution and then store them in a historical database. The historical data is used to initialize and update XGBoost model. In production, keep about past 10 days query stats as the training data with about 7 million records. Besides the model initialization during the service start, the model will also be refreshed every few minutes to include the latest data points. The large enough historical data volume is very critical for the model accuracy, but it also causes model creation and update very slow. To solve this problem, we cut a single giant model into multiple small models, splitting them by the input table query feature. And this split significantly reduced the model creation time and update time. Our workload forecasting service works as a wait station. Before query going into the clusters, we first quickly estimate the query size. As we discussed in the background session, that in ideal case, we want a good isolation between small query and large query traffic, and then handle them differently. Small query performance is very sensitive to the waiting time, while the large query performance is mostly impacted by the amount of the available compute resources. Next, let's see how the query are routed in our production environment after the size estimation is done. Our warehouse query running on Trino could come either from a human user or service pipeline. Normally, we take the query from human user as a higher priority and want to execute them as early as possible, because low query latency is very critical for the data productivity. Service pipelines are less sensitive to the query latency, and they can tolerate some of the waiting time. For small queries from the human users, a dedicated small cluster is created to ensure the high concurrency and the low waiting time. Even though we call this a small cluster, it isn't that small. Actually, the small cluster is still overprovisioned for the small query workload to ensure performance. A large query from human users are routed to the large cluster. This large cluster has majority of the Trino hardware resource and can provide enough compute power for large queries. In the current production, the large cluster is about 5 times bigger than small cluster. For pipelines, both small and large queries will run on the large cluster. They share the resource with human user large queries, but with lower priority than the interactive human user queries. Pipelines queries will run with higher concurrency when the cluster is idle, and lower concurrency when the large cluster is busy. And this is done through the Trino resource group. And meanwhile, we also create a few single node metadata clusters to handle all the metadata queries, such as show tables, reading partitions, and describing table, those kind of metadata operations. And sometimes the estimation could be wrong, and how we can handle the case with incorrect estimations. So for the incorrect estimation, there are two possible scenarios: overestimate or underestimate. When the workload forecasting service overestimate the query, which means the prediction size of the query is a large query, but it actually is a small one. Then the small query could be assigned to run with other large queries in a congested environment. This small query is very likely to wait longer than usual. However, in this case, we won't interrupt the query execution because stop and rerun could make things even worse. After a query finishes the execution, the actual runtime size will be reported back to the workload forecasting service, and then it will make the next prediction more accurate. When we underestimate the query resource, which means a large query is predicted as a small one, running a large query on a small cluster is not a very good thing. It could easily holding the majority of the cluster resource for a very long time and impact all the other small query execution. To avoid this issue from happening, we added the real-time monitoring of the query resource usages. If a query spans more than allowed resource limit, we will stop the execution and take it out and rerun on the large cluster. Next, with the workload management implementation, we can see how we improve our Trino operations. We first look at the overall interactive query performance, which is improved by 40% after the workload management is implemented. As we can see from the chart, the blue execution time changed very little, but queue time dropped significantly. This is because we created a dedicated cluster to prioritize the small interactive queries. They are more sensitive to the waiting time than the amount of resources. So with the small query now prioritized, you may curious what's going to happen to the large queries. The large query performance is also improved by 30%. Different from the overall performance change, large queries now have slightly longer queue time, but because we combine the multiple medium clusters into one single large cluster, large queries now have more resources to execute faster. With slightly longer queue time and much shorter execution time, the overall query execution for large query is still much faster than before. And did we put more hardware resource to make the query faster? The answer is no. Another benefit of merging the medium-sized cluster into a single large cluster is that we no longer have idle cluster at any given time. Better resource utilization and resource sharing greatly improve our cluster resource utilization by 40%. And as a result, we achieved both better performance and lower hardware cost. Our AWS bill on Trino is reduced by 25%. With the workload management, we no longer need to worry about the noisy neighbor and spiky workload problem. And our cluster is much more stable than before, and our on-call workload is reduced about 70%. We also have some future work on our to-do list to further benefit from the workload management. Currently, we only estimate CPU size and peak memory consumption. And next year, we plan to add some execution time estimation to better handle the short query versus long query. Another area we can benefit from the workload management is handling the large queries. This year, we started exploring the fault-tolerant execution and seeing a lot of great benefits using the fault-tolerant execution on supporting large queries on Trino. However, right now at Airbnb, only queries tagged with the fault-tolerant flag are executed in the fault-tolerant mode. We can further improve this user experience by automating the decision on which query should be run on fault-tolerant mode versus which query should run on normal mode, based on our workload estimation. Yeah, that's all we have today. Thanks for being here, and looking forward for the questions.
Yeah, hello. I think we have a few questions that have popped up in chat while you were talking. So the first one from a few minutes ago was just asking about the size of the Trino clusters you're running and goals of minimizing cost overall and how you approach that.
Is that in the chat? Can you repeat that question? I was searching there.
Yeah, so there's the speaker chat and public chat. So that's a question from Saravanan from a few minutes ago.
Oh, I see.
Yeah.
The query routing to the large cluster from pipeline. No, that one.
It's in the bottom. Could we talk about the size of the cluster and
Oh,
how do we minimize cost overall?
Right. We used to have a few medium-sized cluster. Like we have, as I mentioned in the in one of the slides, we have 3 clusters each about 100 nodes. And after the workload management, we combine them together, and we have one small cluster with 50 nodes, the other with 200 nodes. So that's about the size of the cluster. To minimize the cost overall, as I mentioned, is merging the cluster. We found merging the cluster has great benefit on minimizing the cost, mainly because of the resource sharing. So overall, the larger cluster is better than the few medium or small size cluster from the cost perspective.
And besides what Jinyang mentioned,
So another question is, how many query logs are necessary for accurately predicting query sizes? Do you need like 1 day of logs or 1 week of logs or a month?
Yeah, that's a great question. currently we are using about 10 days, 7 million records. That's mainly because we have some weekly pattern that we don't want to miss. For example, if you only keep about 3 days, then you're gonna miss the weekly pattern. For our case, because of the weekly pattern, we keep about 10 days of the query logs. But in case you have a monthly pattern, then you definitely want to keep longer. In my testing, a few million of the records is definitely more than enough to make the query prediction accurate.
Another good question is from Jinyang. Does Airbnb have large ad hoc traffic? So for example, if you have a data scientist running a new random unexpected large query, how does the model handle that, and does that end up working out?
Right. So we do have a lot of ad hoc query from the human users, and based on our model, we're gonna tag them as large query, and they're gonna send to the large cluster but because they are from human users, they are higher priority. So they're gonna take all the resource on the large cluster to speed up the query. So that's how it works. But if no historical stats is provided, that's another good question. So if we have a new query with no historical data sets, then it's going to be an unknown estimation for the first run. So in that case, we're going to run it on the large cluster to avoid congestion on the small ones. But once the query pattern repeats, for example, like the new table is read for the second time, then we're going to have estimation, and then it will based on the query size estimation to route the queries.
Another good question is, do you have auto scaling on these clusters? Oh, Tingting just answered it in chat. So
yeah,
I would say
short answer is we don't have it, but we are exploring it.
Yeah. Okay. It's a lot of different things going on, so that makes sense. That's a good question for Mike. Does the layer of the ML model increase query latency for like small queries that would ordinarily be super fast?
Right. Our P50 of the analyzing the estimation of the query cost is about 20 milliseconds. Sometimes we see 50 milliseconds. So that's pretty small comparing to the user expectation for running a query, offline query on Trino, usually like a few seconds. So the overhead is not that big.
Yeah, that sounds negligible to me. So that's actually pretty quick. That's impressive.
Yeah.
Well, thank you both for your time and for the wonderful presentation.